Okay, so we're going to talk about confidence intervals now. Confidence intervals is one of two classes of types of problems we're going to look at for the remainder of the year. What's really important about confidence intervals is this concept isn't terribly difficult, but we need to make sure that we get the definition correct. And so this idea here we're going to look at is important for us to understand the definition of a confidence interval. So please take good notes here. So the U.S. Mint decides to alter the process for minting next year's penny, but neglects to post the new weight on the website. So we do not know in this case what the mean weight, the average weight of a penny will be. So what we do is we take a sample of 40 pennies, we take n equals 40, and we find that the mean weight of those 40 pennies is 2.8 grams. Okay. And we're going to assume that the standard deviation of pennies is the same as last year's, which was 0.1 grams. Now, which of these numbers is kind of a ridiculous assumption? And the answer is that knowing the standard deviation, when we don't know the mean, it can happen, but it's not real common, right? If we don't know the mean, it's pretty hard to know the standard deviation. Okay, so this idea of being able to assume the standard deviation is 0.1 is a little strange. But we're going to roll with it, and we're going to find ways around that in a little bit. But for now, just keep that in mind that we're going to give you that assumption, but the assumption is a little bit suspect. Okay, so what does our sample x bar look like compared to other x bars? That's the question of what is the sampling distribution looking like? Okay, well, what do we know? We know the sample size is bigger than 30, so we know the distribution is approximately normal. Okay, good. We don't know the mean, but we do know the standard deviation should be 0.1 divided by the square root of the sample size, square root of 40, which is 0.0158. Okay, so the standard deviation of 40 pennies to 40 pennies to 40 pennies should be 0.0158. Let's label that on the graph. So we still don't know the mean. We're going to leave it as a mu. But we know if we go one standard deviation to the right, we have a normal curve. One standard deviation to the right should be mu plus 0.0158. This should be mu minus 0.0158. Okay, this should be mu plus 0.036, right? Mu minus 0.036 roughly. Okay. All right. So 0.046. All right. All right. Point oh, I knew I was doing something wrong. 316. There we go. Mu minus 0.0316. So that's 0.0158 times 2. 0.0158 times 2. Okay, so I go one standard deviation to the right is 0.0158, 2 to the right, 1 to the left, 2 to the left. Okay, this is what we know so far. It's a normal curve because we have n bigger than 30. We know the standard deviation is 0.0158. We don't know the mean. Okay, so the question now is what are the chances that our value of x bar, which is 2.8, is within one standard deviation of the mean? Okay, all right, well, what's the chance on a normal curve that a value is within one standard deviation of the mean? Okay, well, that means that there's a 68, by the 68, 95, 99.7 rule, there's a 68% chance that x bar is in the interval from mu minus 0.0158 to mu plus 0.0158. Now we don't know what mu is, but whatever it is, that's going to be true. There's a 68% chance that 2.8 is in this interval. How about two standard deviations of the mean? Well, that means there's a 95% chance that it's in the interval from mu minus 0.0316 to mu plus 0.0316. Okay, here's the punchline. If this statement is true, then it is also true that there's a 95% chance that mu is in the interval from 2.8 minus 0.0136 to 2.8 plus 0.0316. Okay, now I've taken a little shortcut here with some of the language, but I want to make the point here that this is basically the idea. If there's a 95% chance that 2.8 is within 0.0316 units of the mean, so if there's a 95% chance that x bar falls within 0.0316 of mu, then there's also a 95% chance that mu falls within 0.0136 units of 2.8. So what that means is that there's a 95% chance that this interval contains mu. Okay? 95% chance that that interval contains mu. Okay, so if you look at it, and I'll go ahead and quickly 2.8 minus 0.0316, 2.76, 2.83. There's a 95% chance that this interval contains the real average weight of a penny. Okay. All right. Let's look at some definitions here. A confidence interval and a confidence level. So a confidence interval has two parts. A confidence interval is calculated from the data, and usually what we start with is an estimate. That was like our 2.8. Give or take a margin of error. In this case, it was our 0.0316. So we had, in our case, it was 2.8 plus or minus 0.0316. And that's coupled with a confidence level, which in our case was 95%, which gives the probability that the interval will capture the true parameter in repeated samples. Okay? It's like a success rate for the method. So for instance, in our case, let me go back to the previous slide real quick. In our case, our interval is 2.76 to 2.83. What that means at 95% confidence is that there's a 95% chance that based on our sample, we produced an interval that somehow contains the real average value. 95% of the time, if we do this method, we're going to create an interval that will contain the true mean. 5% of the time, we're going to create an interval, and that interval will not contain the true average weight of a penny. Now, we never know which one we have, but we do know there's a 95% chance that we've got the right one. Okay. All right. So a little bit, some notes here. The construction of a confidence interval for a population mean is appropriate when the data comes from a simple random sample, the sampling distribution is normal, or normally distributed, approximately, and we have independence. Okay, that same 10 times n business where the sample is smaller than 10 times, the population is larger than 10 times the sample size. Okay, so these two things are going to make it happen. Now, one thing I want to point out here, that a really important concept when you're doing the homework here, is that this confidence level, the 95%, is the probability that the interval will capture the true parameter. It is not the probability that the parameter is in the interval. Okay. Now there's a distinction here, and that when I say the probability that the parameter, that mu, falls inside the interval, I'm implying that mu can change. Mu is fixed. We just don't know what it is. The interval that we create can change depending on our sample. Okay, so just chew on that for a bit. All right, here is the actual nitty-gritty of the formula. Now, a confidence interval for the population mean, when we know the standard deviation, is given by this formula. We take our estimate plus or minus z star, we'll talk about that in a moment, I'll just call it z star, times the standard deviation divided by the square root of n. So if we look at our particular example, it was 2.8 plus or minus, we had 0.1 divided by 40. That gave us our standard deviation. And the number we put here was 2. Our z star was 2. Now, that came from the 68, 95, 99.7 rule. Z star of 2 gave us the fact that implied we had 95% confidence. Okay, it's a z-score to the right and to the left. Okay, it's the area between the z-score from the left to the right. Okay, to find the z-score values when you're doing these problems, everything else you can find, to find the z-score values, you're going to go into Table A and look on the, I believe it's the bottom row. I'll pull up a copy of that in a moment and show you how to find the z-scores. Now, for 95% confidence in the book, you're going to find that z star equals 1.96, which is really the exact value. I was using 2 to make the problem easier for us to think about when we were doing it. So Table C says T distribution critical values. Now, at this point, we're not going to worry about that. Instead, we're going to look down at the bottom row down here. Okay, so we need to look at Table C in your textbook. We want to go all the way down to the end of Table C. And if I want a confidence level of 95%, I need to go up to 1.96 right here, the z star row in the table. So I look down here. If I want 95%, my z star value is 1.96. If I want 99.5%, my z star value is 2.807. And that's how we find the appropriate z star value for a particular level of confidence that we want. So z star controls the confidence level. Everything else is given to you in the problem. Okay, so hopefully this will be enough for you guys to do your homework. Good luck.